I have explained that when a charge is placed in a magnetic field, it experiences force as well as it possesses electric potential energy. Now, what happens if a pair of unlike charges are placed in an uniform electric field? So, let us consider a uniform electric field E, and I am going to consider a pair of equal and opposite charges. But a pair of equal and opposite charges represent an electric dipole, and the separation between the dipole is taken as a 2A, and in the presence of electric field, both these two charges experiences force. A positive charge experiences force in the direction of electric field, a negative charge experiences force in the opposite direction, so that the net force is 0. But these two forces, they represent equal and unlike parallel forces, which represent a couple, and when couple acts on a body, it experiences a torque, which is tau. And in our earlier discussion, we have proved that this torque experienced by this dipole is given by P E sin theta, where what is P? It is electric dipole moment. It is a vector quantity which is directed from negative to positive charge. So, this is the direction of the dipole moment. E is an electric field which is indicated as shown in the diagram. And what is the theta here? Theta represent the angle between the electric field vector and the dipole moment vector. So, what happens when it experiences torque? When it experiences torque, it gets rotated in the direction of the field, and this entire dipole is get arranged like this. It is get aligned in the direction of the electric field. So, this is called stable equilibrium position. So, the direction of rotation here is clockwise. I am going to exert an external torque in the anticlockwise direction, and I will maintain the dipole in this position. So, when I maintain the dipole in this position, the torque acting, magnitude of the torque acting is given by tau is equal to P E sin theta. From this position, if the dipole is further rotated by a very small angle d theta, so that the total angle is theta plus d theta. In rotating the dipole further by an angle of small d theta, small angle d theta, so I have done work. So, what is the work done in rotating the dipole through a very small angle? That is given by dw is equal to tau into d theta. Now, this comes from the expression dw is equal to f into ds. This is in the linear motion and this is in the rotational motion of a body, where tau is given by P E sin theta, P E sin theta into d theta. So, this is the small work done in rotating the dipole from the position which I have maintained further through a small angle d theta. So, if I have to calculate the total work done in rotating the dipole from any one position, okay, which makes an angle, initial angle theta 1 to a new position which is a theta 2, then the total work done is given by integrating this value of dw with the limits theta 1 to theta 2 and dW, that gives Pe sin theta d theta. So, on integrating we get total work done in rotating the dipole from initial position, which makes an angle theta with the electric field, to the final position theta 2, that is also an angle made by the new position with respect to the electric field. So, here P is a constant which we can write outside, integrating between the limits theta 1 and theta 2 sin theta into d theta, that is Pe. Integration of the sin theta d theta is minus cos theta under the limits theta 1 and theta 2. So, that is Pe into minus cos theta 2 minus of minus cos theta 1. Right. So, that gives the final expression as Pe into cos theta 1 minus cos theta 2. So, this is the expression for work done in rotating a dipole of dipole moment P in an uniform electric field E from an initial position theta 1 to a final position theta 2. Now, what if the dipole is initially in the stable equilibrium position? If the dipole is initially in the stable equilibrium position, in that case this theta 1 will be 0, theta 1 is 0. From this stable equilibrium position, if it is rotated to a new position which makes an angle theta, then theta 2 will be equal to theta. So, on substituting those angles here, I am going to get an expression W is equal to Pe into cos 0, which is 1 minus cos theta. So, this is the general formula, and that is a special case where we can make use of this formula only when we rotate the dipole from stable equilibrium position to a new position. The stable equilibrium position is one where the dipole is get aligned in the direction of the electric field. So, let us consider the various cases out of it. Suppose if the dipole is rotated from the stable equilibrium position to a new position theta, then the work done is given by Pe into 1 minus cos theta. Now, what if theta is 0 degree? Theta 0 means the dipole is not rotated at all, because it is already in the stable equilibrium position, that is theta is 0, and then it is not rotated because theta, again I have taken this as 0. So, what is the work done in this case? So, when theta is 0, we get cos 0 1, so we get W is equal to 0. That is, no work is done in rotating the dipole. Now, what if the dipole is rotated through an angle of 90 degree? From the stable equilibrium position, it is rotated through an angle of 90 degree. Cos 90 is 0, so we are going to get W is equal to Pe. Now, what if the dipole is rotated through 180 degree? It is in the stable equilibrium position, it is further rotated through an angle of 180 degree, which we call the unstable equilibrium position. So, cos 180 degree will get minus 1. So, 1 minus of minus 1 will get 2. So, therefore, here W is equal to 2 Pe. So, these are the special cases that we can get out of this expression. So, expression for work done in rotating the dipole in an uniform electric field from one position to another is given by W is equal to Pe into cos theta 1 minus cos theta 2. So, I am going to rearrange this equation. W is equal to minus Pe cos theta 2 minus of minus Pe cos theta 1. As we know from work energy theorem, work done is equal to change in energy. That energy can be in any form, potential, kinetic. So, if I consider this term as the final and if I consider this as the initial, then what we get to find here is work done is equal to change in potential energy, where this term represent the final potential energy and this term refers the initial potential energy. Therefore, the potential energy stored in an electric dipole is of the format minus P E cos theta, where P is the electric dipole moment, E is the uniform electric field and theta is the angle between dipole moment and the electric field. So, here we have two vectors, dipole moment is a vector, electric field is a vector, but energy is a scalar, and since it is a function of cos, it is very easily we can write that potential energy is the dot product of negative dot product of dipole moment and electric field. So, taking various cases out of it, if I consider theta 0, I am going to get U is equal to minus Pe. When theta is 90 degree, cos 90 becomes 0 here. So, we get U is equal to 0, and when theta is 180 degree, U is equal to cos 180 minus 1, we get plus Pe. So, we find that when the dipole is in the stable equilibrium position, its energy is a negative. So, its energy is the least. So, energy is minimum when the dipole is in the stable equilibrium position and its energy is maximum when it is in the unstable equilibrium position. So, just to revise the various equation, starting with the torque experienced by dipole in an electric field is given by tau is equal to Pe sin theta, or in vector form vector tau is equal to cross product of vector P and vector E. Work done in rotating the dipole from one position to another position in an uniform electric field is given by W is equal to Pe into cos theta 1 minus cos theta 2. Work done in rotating the dipole from the stable equilibrium position to a new position is given by W is equal to Pe into 1 minus cos theta, and energy stored in an electric dipole is given by U is equal to minus Pe cos theta, or U is equal to minus the dot product of vector P and vector E. And if you consider the energy stored in the two charges in the electric field, then the net energy is also given by minus Pe cos theta and then minus 1 by 4 pi epsilon naught q square by 2a. That is, if the two charges, that is minus q and plus q, are separated by 2a, then the potential energy due to these two charges is given by the format U is equal to 1 by 4 pi epsilon naught product of the two charges and the separation between them. So, I have used this form in writing this equation. It is minus 1 by 4 pi epsilon naught q into q, q into minus q will give you here minus sign q square, and by the separation which is 2a. So, this is the net energy, net potential energy stored in the dipole. From the discussion of the earlier two chapters, we have concluded few facts regarding the electrostatic. So, one of such fact is, inside a charged conductor, electric field is always 0, and the charges, they get accumulated at the sharp ends where the curvature is more or radius of curvature is less, and electric field is 0 inside any charged conductor of any shape. We have proved in the case of spherical shell E is 0 using Gauss theorem, but that is valid for charged conductor of any shape. These charges in static equilibrium, they get rearranged in such a way that the electric field inside is a 0, and this is true even if there is a cavity where electric field is always 0. So, this in the cavity, if we place any object, it is free from the electrical influence of the external field, and that is why this is called electrostatic shielding. And this concept can be used to protect the electrostatic apparatus by placing inside any metal structure, so that it is free from the influence of the external electric field. The third one, when the electric field inside a conductor is 0, we can find the potential inside using the relation between the electric field and the potential. Electric field is always is equal to the negative potential gradient. When E is 0, minus dV by dx is 0, that is derivative is 0. Derivative of any quantity is 0 provided that quantity is a constant. So, that is why potential inside any conductor is constant, but potential difference is 0, but potential is always constant, but electric field is also 0 here. E is 0 and potential difference is 0, but not electric potential. Potential is a constant and it is same as that on its surface. So, what is the potential difference on the surface of the conductor? It is 0, but potential at a point on the surface as well as inside is always a constant. In the case of charged conductor, electric field is always normal to the surface of charged conductor. Let us assume that it is not normal. If it is not normal, then it has a component along the normal as well as along the tangent. So, if this is theta, this component tangent to the surface of the conductor will be E cos theta, and along this it will be E sin theta. And if there is a component along the tangent to the surface, then the charges here experience force due to this component E cos theta, which is given by F is equal to the charge present, which I am going to write it as dq, into E cos theta. But we find that in static equilibrium these charges, they do not move, which means F is 0. and when f is 0, dq and E cannot be 0 because there exists a field. So, cos theta has to be 0, and cos theta is 0 means theta has to be 90, and when theta is 90 degree here, we find that this electric field has to be along the normal, and that proves that the electric field or the lines of force, they are always normal to the surface of the charged conductor. If we take charged conductor, the excess of charges, they always reside over the surface of the conductor, and no charges will remain inside the conductor. So, that can be proved even by taking a small volume element delta V. What is the electric field inside this volume element? Electric field is always 0, and we know that the electric flux is given by E delta S cos theta, and when electric field in that volume element is 0, this E has to be 0. When E is 0, delta phi is also 0. So, let us apply the Gauss theorem. Delta phi is equal to 1 by epsilon naught into delta q, and since the flux is 0, this delta q has to be 0, which proves that no charges will remain inside the charged conductor, they will reside only on the surface of it. So, we can find electric field due to charged conductor of any shape. So, here we have part of a charged conductor, and I want to find the electric field at a point very close to the charged conductor, and I am going to use the Gauss theorem in finding the electric field. Let us consider a small area around this point, and this area I am going to extend it within the conductor, so that a Gaussian surface in the shape of a pillbox is taken. Point P lies outside and point Q lies inside the conductor. These charges are uniformly distributed, so that delta Q is the amount of the charges enclosed by this Gaussian surface within an area of delta S, so that we can find the surface density of the charge at that point. Sigma is equal to delta Q by delta S, so that the charge enclosed is delta Q is equal to sigma into delta S. The electric field is always normal to the surface of the conductor, and it is outward because the charges are positive. So, what is the flux through this Gaussian surface with this, which is in the shape of a pillbox? There is no flux through the end face containing Q, because it is inside the conductor. There is no flux through the lateral surface of this pillbox, because the lines of force are normal to the surface of the conductor. Therefore, the flux through the end face containing P can be calculated using delta phi is equal to E delta S cos theta. The area vector to the surface is also along the electric field. This is the area vector. So, therefore, the angle between the electric field and the area vector is 0, and cos 0 is 1. Therefore, the flux is given by E delta S. Now, using Gauss theorem, the flux is given by 1 by epsilon naught times the charge enclosed within the Gaussian surface, which is delta Q. That is 1 by epsilon naught into the charge enclosed is sigma into delta S. So, using this equation, we can equate E delta S is equal to 1 by epsilon naught into sigma into delta S. Therefore, electric field is given by sigma by epsilon naught. If you want to write in vector form, E vector is equal to sigma by epsilon naught. You can introduce a unit vector which is in the direction of electric field. So, this is expression for electric field due to a charge conductor. Polar and non-polar dielectrics. So, first, what are polar molecules? If I take example of carbon monoxide or water, sulfur dioxide, hydrogen chloride, then we have nitrous oxide. In all these molecules, the center of positive charge and center of negative charge, they do not coincide. Such molecules are called as polar molecules, and the dielectrics which are made up of polar molecules are called as polar dielectrics. So, water is a good example for polar dielectric. In oxygen, nitrogen, hydrogen, we have methane, we have benzene C6, HO6, and then we have carbon dioxide. In all these molecules, the center of the positive charge and the center of the negative charge, they coincide, and such molecules are called as non-polar molecules, and the dielectrics made up of non-polar molecules are called as non-polar dielectrics. So, oil is a example for non-polar dielectrics. Now, if we introduce these polar or non-polar dielectrics in an electric field, what happens next? Students, in chapter 1 we have learned that when we introduce a dielectric in an electric field, the strength of the field decreases. So, what is the reason for that? To understand that, so let us refer this diagram here. We have polar dielectric and non-polar dielectric. As I have mentioned, polar dielectrics are the dielectrics which are made up of polar molecules, in which the center of the positive and the center of the negative charge do not coincide, and non-polar dielectrics are made up of non-polar molecules, in which the center of the positive and center of negative charges, they do coincide. Now, when we consider one molecule of a polar dielectric, since their centers of the charges are they do not coincide, every molecule possesses a dipole moment which is directed from negative to positive. So, let P be the dipole moment of every molecule which is directed from negative to positive. Negative to positive. So, what is the net dipole moment of this entire dielectric, which is the vector sum of the dipole moment due to individual dipole. But here, due to the thermal agitation, they are randomly oriented. So, for every dipole moment in one direction, there will be another molecule having dipole moment in the opposite direction, like this. So, they cancel each other. So, that is why if we consider the net dipole moment of the entire system, it is 0. So, that is in the case of polar dielectric. And non-polar dielectric, so we know that since their centers, they coincide each other, the net dipole moment of the entire system is 0, because it is a 0 for even each molecules. Let us see what happens when we introduce such dielectric in an electric field. So, I am going to take an arrangement where we have oppositely charged parallel plates. separated by a very small distance, and plus sigma is the surface density of charge of the positively charged plate, minus sigma is the surface density of the negatively charged plate, so that it produces an uniform electric field directed from positive to negative. And I am going to consider that as E naught, and the value of that E naught is given by sigma by epsilon naught. So, at present I am going to assume that the space here is a vacuum, and this is expression for the electric field when no medium is introduced between the oppositely charged parallel plate. And now we are going to introduce one of the dielectric. Let us consider the polar dielectric, and when we introduce this polar dielectric in an uniform electric field, every dipole is under the influence of electric field. So, it experiences a torque, due to which these dipoles, they get oriented in the direction of the electric field, and we get to see that in this diagram. So, these are the dipoles which experiences torque, and then they get aligned in the direction of the electric field. Now, what is the direction of the dipole moment for every dipole? It is from negative to positive. As you can see, every dipole attains dipole moment in the same direction, so that this entire dielectric, it possesses certain net dipole moment, which is equal to number of molecules into the dipole moment of the each molecule. It is a vector sum, and since they are all in the same direction, we can multiply by the number of molecules. So, this is the net dipole moment attained by every dipole. Since the positive center of one of the molecule is very close to the negative center here, their effect is get neutralized, or it is a minimum, and that leaves only a set of negative charges at one end and set of positive charges at the other end of the dielectric, and that creates an electric field within the dielectric in a direction opposite to that of the external electric field, and that electric field is directed from positive to the negative, which I am going to write it as E suffix I. The strength of this electric field will be lesser than this E naught, and due to these positive charges, we can measure the surface density of the charges accumulated here, which I am going to write it as sigma p. This is plus sigma p, here we have minus sigma p, so that we can find the strength of that electric field EI, and that EI is given by sigma p by epsilon naught. And when we place the dielectric, and when these dipoles are get oriented, we say that this dielectric is polarized. So, that is why this sigma p is the surface density of the polarized charges, and the direction of the electric field is opposite to the applied electric field. So, since these two fields are in opposite direction, the resultant electric field E suffix m I am going to write, that is in the presence of a dielectric medium, is equal to the net electric field, and since the angle between them is 180 degree, it is E naught minus EI. What is E naught is equal? It is a sigma by epsilon naught. What is EI? That is equal to minus sigma p by epsilon naught. So, therefore, the net electric field between the two oppositely charged parallel plate, it is given by sigma minus sigma p by epsilon naught. So, which will be lesser than the earlier electric field, because EM is E naught minus EI. So, the reason for decrease in the electric field is because of the dielectric polarization. We can even find the value of the dielectric constant here, which is given by epsilon r is equal to the ratio of the electric field without the dielectric to the electric field in the presence of the dielectric. That is equal to E naught is sigma by epsilon naught by Em here sigma minus sigma p by epsilon naught. So, we get dielectric constant is equal to sigma divided by sigma minus sigma p. From this, sigma minus sigma p is also given by sigma by epsilon r, and that we can replace here, so that we can find the net field Em is equal to sigma divided by epsilon naught into epsilon r. So, this is the expression for net electric field between the two oppositely charged plates. Now, what happens if we introduce a polar dielectric between the two plates? In the absence of the electric field, the centers of positive and negative charges, they coincide. But in the presence of the electric field, the centers are under the influence of the electric field, so they get shifted by a very small distance. And when they get shifted by a very small distance, now these non-polar molecule, now they behave like polar molecule. That is only in the presence of the electric field. And because of the separation in their center, they produces a dipole moment in the direction of the electric field, and like earlier, they create a field in a direction opposite to that of the external electric field, so that we can apply the same theory as I have explained here. So, only difference is in the case of polar dielectric, the electric field that is created inside is because of intrinsic dipoles, whereas in the case of non-polar dielectric, the electric field that is created is because of the induced dipoles. That is why that E suffix I can be considered as electric field due to the intrinsic dipoles, or here it is because of the induced dipoles. So, irrespective of the polar or non-polar dielectric, electric field between the plate always reduces, and that is because of the polarization. And we say that the dielectrics are polarized in the presence of external electric